Greetings, everyone. Learning as a hobby here. I wanted to make my video on my solutions for exercise set 3.5 in Terrence Tao's Analysis 1 book. So that's what I'm going to do. Let me bring up my solutions and we'll go through them. All right, and this, just so you know, this problem set is a bit longer than the other ones, so it might take me a little while to get through all the problems, but just bear with me. I'll try to go, reasonably fast without too fast, so that people can at least people can understand my solutions. So let's start with the first one, 3.5.1. Part 1 says there's a few parts to this. Part 1 of question 3.5.1 says, suppose we define the ordered pair xy for any objects x and y by the formula xy equals the pair set containing the singleton set x and the pair set xy, thus using several applications of axiom 3.4. Then he gives a few examples of it, and he says, show that such a definition, known as the Kuratowski definition of an ordered pair, indeed obeys the property 3.5. We've actually done this problem already in one of the appendices in section 1 of Spivak's book. What I don't, maybe you saw that video on my channel and maybe you didn't, but I'm going to go through it again anyway. So let's actually do that. So I broke this up into two cases. Case A is assume xy is equal to x prime y prime, where x is not y and x prime is not y prime. Then the pair set containing the singleton set x and the pair set xy is equal to the pair set containing the singleton set x prime and the pair set x prime y prime. That's just by the way we defined the ordered pair up above, all right? The Kuratowski definition, as he calls it. Then the singleton set x is an element of the pair set containing the singleton set x and the pair set x comma y, which implies that the singleton set x is an element of the set on the right, the pair set on the right, which implies that just by using the definition of what it means for an element to be, for something to be an element of a pair set, that means that the singleton set containing x is equal to the singleton set containing x prime, or the singleton set x is equal to the singleton set, the singleton set x is equal to the pair set x prime y prime. However, the singleton set x cannot actually be equal to the pair set containing x prime y prime, because this would imply that that this pair set x prime y prime is a subset of the singleton set x, which would imply that x prime equals y, x prime equals x and y prime equals x, but that can't happen because we already assumed at the beginning that x prime was not y prime. Therefore, the singleton set x equals the singleton set containing x prime, which implies x equals x prime. Then the pair set x comma y is an element of the pair set containing the singleton set x prime and the pair set x prime y prime, which implies that the pair set xy is equal to the singleton set x, which can't happen since x is not x prime. X is not y, or the pair set xy equals the pair set x prime y prime, which implies that y equals y prime since x is equal to x prime. Right, and then case B is when the two entries are the same. So let the ordered pair A comma A equal the ordered pair B comma B. Then the singleton set containing the singleton set A is equal to the singleton set containing the singleton set B. I'm getting tongue-tied here, which implies that the singleton set containing A is an element of the singleton set containing the singleton set containing B, which implies that the singleton set containing A equals the singleton set containing B, which means that A equals B. Therefore, 3.5 is satisfied, which is what he wanted us to show. Okay, so that's the solution for part 1. Part 2. We're going to define it in a different way. Suppose we instead define an ordered pair using the alternate definition x comma y equals the pair set containing X, and then the pair set containing X comma Y. Show that this definition, which he calls the short definition of an ordered pair, also verifies 3.5 and is thus also an acceptable definition of an ordered pair. He also gives a warning here. He says this is tricky. One needs the axiom of regularity, and in particular, exercise 3.2.2. So let's go through the proof. Right, assume the short definition for an ordered pair and let xy equal x prime y prime. Then the two pair sets here that I've written here are equal to each other. Then x is an element of the pair set containing x, and the pair set containing x comma y implies x is an element of the pair set containing x prime and the pair set containing x prime y prime, which implies x equals x prime, or x equals the pair set containing x prime y prime. Then I guess here I'm going through some cases. Case A, if x is not a set, then that means that x has to equal x prime, because if it were equal to x, the pair set containing x prime y prime, then it would be a set, right? So that implies that the pair set xy equals the pair set x prime y prime, which implies that y is an element of x prime y prime, which means that y equals y prime. So that checks out for that case. Then case B, if x prime are sets and x equals x prime, then either x equals x prime equals y prime, or x is not y prime. In either case, x is not the pair set containing x prime y prime by regularity. By regularity, I mean by the axiom of regularity, which implies that the pair set xy equals the pair set x prime y prime, which implies that y equals y prime. Right, and then case C, if x equals the pair set containing x prime y prime, then x is not x prime by regularity. Then the pair set containing x and the pair set x comma y is equal to the pair set containing x prime comma x prime y prime, the pair set containing x prime y prime, which is equal to the pair set x prime comma x, because x equals x prime, right? Sorry, because x equals x prime y prime, sorry, the pair set containing x prime y prime, which implies that x prime is xy, but that contradicts exercise 3.2.2. Therefore, x equals x prime and y equals y prime. If you we went over, he refers back to a lot of different things, and rather than like actually bring them up in the video over and over again, because there's a lot of that, this video will be like 3 hours long if I go back and forth. So you can look that up in the video that I did for section 3. Section 3.2, the solution set for 3.2, because I did that problem there. So you could look back at it in the video. Okay. Question. So that, I should say that therefore, 3.5 is satisfied. Maybe I should actually write that. Let me do that here. Okay, last part of question number 1. Show that regardless of the definition of ordered pair, the Cartesian product x times y of any two sets xy is again a set. And he gives a hint here. He says first use the axiom of replacement to show that for any x and x, that the set containing the ordered pairs x comma y, where y is an element of y, is a set, and then apply the axiom of union. All right, so here's my proof. Let x and y be sets. Define the family of sets AX, where x is an x, where AX is the set that he talks about above. So the set of ordered pairs x comma y, where y is an element of y for each x and x. Then AX is a set for each x and x by the axiom of replacement. Then the union of all the sets AX for x and x is a set by the axiom of union. And for any ordered pair xy, xy is an element of AX, implies xy is an element of the union. Also, if A is an element of the union, then A is an element of AX for some x and x, which implies that A is x comma y for some y and y, which implies that A is an ordered pair whose first component is in x and whose second component is in y. Therefore, the union here equals the set of all ordered pairs x comma y, such that x is an x and y is an y, and x times y equals that union is a set. All right, so that's question number 1. Question 3.5.2, he refers to a footnote here, so let me actually read that to you. Actually, let me read the definition first, and then I'll read the footnote. So he says, suppose we define an ordered n tuple to be a surjective function x from the set I in n, such that I1 is less than or equal to I is less than or equal to n to x, whose codomain is some arbitrary set x. So different ordered n tuples are allowed to have different ranges. We then write x sub I for x of I, and also write x as the ordered n tuple, the finite sequence xi. Using this definition, verify that we have the two finite sequences are equal if and only if xi equals yi for all I between 1 and n. Also show that if the sequence xi are, here xi are sets, show that if the sequence of xi are an ordered n tuple of sets, then the Cartesian product as defined in definition 3.5.6 is indeed a set. He also gives a hint here. He says use exercise 3.4.7 and the axiom of specification. But before I get to my proof, let me just read the footnote to you guys that he has on page 67. Okay, let me see, where is it? So he says technically this construction of ordered n tuple is not compatible with the constructions of ordered pairs in exercise 3.5.1, but this does not cause a difficulty in practice. For instance, one can use the definition of an ordered two tuple here to replace the construction in exercise 3.5.1, where one can make a rather pedantic distinction between an ordered two tuple and an ordered pair in one's mathematical arguments. So that's the footnote that he refers to here when he says, suppose we define. So let's go to my proof. Okay. Part here, case one, let xi equal yi. Then for any I where I goes from 1 to n, xi is equal to x of I equals yi equals y sub I by equality of functions. Next, if xi equals yi for each I between 1 and n, then xi equals x sub I equals y sub I equals y of I for each I between 1 and n, then that means that the two sequences are equal to each other, right? And then case two, which is the second part that he's asking about here, where we have a sequence of sets. Let A be the set of all partial functions from the set I and n, where I goes from 1 to n, to the union of xi's, I going from 1 to n. Here we're using that problem, what was the number, 3.4.7. We're going to use the fact that this gives us a set. Well, let me not. I was going to say I actually did that problem, which I left out in the last solution set video, but I'll show that to you in a minute, because when we prove axiom 3.11 from lemma 3.4.10, I think it was, I skipped that problem in the previous problem set, but I proved it here, so I went back and I did the problem that relies on that exercise. Sorry, we'll get around to that. So here I'm assuming the result from exercise 3.4.7. All right, A is guaranteed to be a set from exercise 3.4.7. Let B equal the set of all x in A, such that x of I is an element of xi for all I between 1 and n. Then B is a set by the axiom of specification, which implies that the Cartesian product of the xi's, I going from 1 to n, is equal to B as a set. All right. Question 3.5.3. Show that the definition of equality for ordered pair and ordered n tuple are consistent with the reflexivity, symmetry, and transitivity axioms, in the sense that if these axioms are assumed to hold for the individual components xy of an ordered pair x comma y, then they hold for the ordered pair itself. All right, so let's go through the proof. And actually, let me just readjust because my leg is falling asleep here. All right, let's do them one at a time. So reflexivity first. X1 equals x1 dot 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 up to xn equals xn for all I 1 through n implies that x equals x, so reflexivity is pretty straightforward. Symmetry, let x equal y, then x1 equals y1, dot, 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 up to xn equals yn for all I 1 to n. Then we could just, use symmetry of equality of numbers, right, from the equality of numbers. That means that y1 equals x1, dot, 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 up to yn equals xn for all I from 1 to n. So that means that y equals x. So symmetry holds. And then finally, transitivity. Let x equal y and y equal x. Then, I'm sorry, this should not be y equal x. It should be y equals z. So that's a typo. All right, then xi equals yi and yi equals zi for all I 1 to n. So xi equals yi equals zi, which implies that xi equals zi for all I 1 to n. Therefore, x equals z. And I just realized I probably didn't I didn't define these for you, but x is the ordered n tuple x of the xi's, y is the ordered n tuple of the yi's, and z is the ordered n tuple of the zi's. Right, so that shows the transitivity holds, and the other two also hold. So that's it. All right, question 3.5.4. Let A, B, C be sets. Show that the Cartesian product of A with B union C equals the Cartesian product of A with B union the Cartesian product of A with C. And then these other set identities as well. He says one can, of course, prove similar identities in which the roles of the left and right factors of the Cartesian products are reversed. This is just a generic, set proof. So I'll scroll through it kind of quickly again, because we've done like a million of these already. And like I said, to show that one side equals the other side, you just show that the left is a subset of the right and the right is a subset of the left. So I'll scroll through it quickly if you want to pause your screen and read the solution, but I'm not gonna, belabor the proof here. That it's very, very straightforward. All right, so here's the proofs. So like I said, you can pause your screen if you want to see. All right, so those identities hold. 3.5.5. Let A, B, C, D be sets. Show that A times B intersects C times D is A intersects C times B intersect D. And then he says, is it true that A times B union C times D equals A union C times B union D? And he says, is it true that A times B minus C times D is equal to A minus C times B minus D? All right. And the proof of the first thing, again, it's same type of proof. So I'll let you here. I'll just leave it on the screen here for a second. You can pause your screen and see the proof here. I'm not going to go through it in detail. But 2 and 3, I do want to mention. So A times B union C times D is not in general equal to A union C times B union D. For example, if A is the set 1, 2, B is the set 3, 4, and C is the set 5, 6, and D is the set 7, 8, then 5, 4 is an element of A union C times B union D, but 5, 4 is not an element of A times B union C times D. All right, so that's a counter example. And 3, A times B minus C times D is not in general equal to A minus C times B minus D. And again, I just have a counter example here. So if A is the set 1, 2, B is the set 3, 4, which is equal to the set D, and C is equal to the set containing 5, 6, then the ordered pair 1, 3 is an element of A times B minus C times D. But 1, 3 is not an element of A minus C times B minus C, since A minus C times B minus D is the Cartesian product of A with the empty set, which is the empty set. All right, question 356. Let A, B, C, D be non-empty sets. Show that A times B is a subset of C times D if and only if A is a subset of C and B is a subset of D, and that A times B equals C times D if and only if A equals C and B equals D. And he wants us to say what happens if some or all of the hypotheses that A, B, C, D are non-empty are removed. All right. Again, this is one. I'll just pause my screen on here and you can look at it yourself. It's, you just to show that something is a set is a subset of another, you just show that an arbitrary element of the first set is always an element of the set on the right. And for equality, you show inclusion both ways. So here you can, like I said, you can pause the screen and see, but I won't go through it in detail. All right, 3.5.7, let xy be sets and let pi from pi subscripted x times y to y from x times y to y, and pi subscript x times y to y from x times y to y be the maps. These are called coordinate maps. So pi x times y to y takes the ordered pair xy to the first component or the first coordinate x, and the other one takes the ordered pair xy to the second component. He says these are called coordinate functions, or sometimes you might hear them referred to as projections. So projected onto for either the first or second coordinate space. Show that for any functions f from z to x and g from z to y, there exists a unique function h from z to x times y, such that pi subscripted x times y to x composed with h is equal to f, and pi x times y to y composed with h equals g. And he says compare this to the last part of exercise 338 and exercise 317. I didn't really say anything about that, but you should look back and see similarities and things. This function h is known as the pairing of f and g and is denoted h equals f comma g. All right, so here's my proof. Let h from z to x times y, such that for z and z, h of z is the ordered pair f of z, g of z. Then if you take the projection on the first coordinate composed with h of z, that gives you f of z, just by the way we define the functions, and the projection onto the second coordinate composed with h of z gives you g of z. So it works. Furthermore, assume that h prime is another function that does that for any z and z. Then you can see that actually the function for each input value, the function values are the same, so they're the same function. All right. Okay, 3.5.8. Let x1 through xn be sets. Show that the Cartesian product x of the xi's, where I goes from 1 to n, is empty if and only if at least one of the xi is empty. So assume that x1 through xn are all non-empty sets for I 1 to n. Then we can take x1 through xn, where xi is an xi for I1 for between 1 and n by finite choice, which is lemma 3.5.11, I think. Then that implies that the sequence x sub I is an element of the Cartesian product, is not empty, because there's something in it, right? Next, if at least one xi is empty, then without loss of generality, we can assume that x1 is the one that's empty. There may be other ones that are empty too, but at least one of them, we can assume is empty, which is x1. Then x1, the Cartesian product of x1 with x2 and so on up to xn is equal to the set of finite sequences, xi's, where I goes from 1 to n, where xi is an xi for I going from 1 to n. But that implies that x1 is an element of x1, which contradicts that x1 is empty. Therefore, the Cartesian product must be empty. All right, 3.5.9. Suppose that I and j are two sets, and for all alpha in I, let A alpha be a set, and for all beta in j, let B sub beta be a set. And then he wants us to show that the arbitrary union of the family of A alpha intersect with the arbitrary union of the family of B betas is equal to the arbitrary union of the intersections of the A alphas with the B betas. And what happens if one interchanges all the unions and intersection symbols here. Again, this is a proof where you show one set is equal to another. I'm not going to go through that again because if you're doing these problems, you understand why. It just gets kind of tedious. But so here, again, if you want to look at it, I'll just scroll through it slowly so you can see. But you just show that one side is a subset of the other, and then the other side is a subset of the first. All right, and then if you interchange all the unions and symbols, you still get equality. So I proved that here in part 2. Okay, and let's see, 3.5.10. If f from x to y is a function, define the graph of f to be the subset of x times y, defined by the set of all ordered pairs x comma f of x, where x is an element of x. There's a few parts to this. So part one says show that two functions f from x to y, comma f tilde from x to y are equal if and only if they have the same graph. So here, let's do it both ways. So because it's if and only if, right, by conditional. Let f equal the function f tilde. Then then by definition, the domains and codomains are the same, and also f of x equals f tilde of x for each x and x. So the ordered pairs x comma f of x equals the ordered pair x comma f tilde of x, which implies that the graphs are the same. And then you show that the graphs being the same shows that implies that the functions are the same. So if the two graphs are equal to each other, then for any x and x comma f of x equals x comma f tilde of x, which implies that f of x equals f tilde of x for each x and x, which means that f is f tilde. All right, part two. Conversely, if G is any subset of x times y with the property that for each x and x, the set y in y such that xy is in G has exactly one element, or in other words, G obeys the vertical line test, show that there's exactly one function f from x to y whose graph is equal to G. Right, here's my proof. Clearly, G is the graph of a function since it satisfies the vertical line test. Let f from x to y and f tilde from x to y be two functions whose graph is G. Then f equals f tilde follows from part one. All right, and then part three, suppose we define, I put a star here, which means that he has a footnote here. So maybe I'll read out the problem and then I'll read the footnote after I read out the problem, and then we'll look at the proof. So part three says, suppose we define a function f to be an ordered triple, f equals xyg, where xy are sets and g is a subset of x times y that obeys the vertical line test. We then define the domain of such a triple to be x, the codomain to be y, and for every x and x, we define f of x to be the unique y in y such that xy is an element of G. Show that this definition is compatible with definition 331 in the sense that every choice of domain x, codomain y, and property p of xy obeying the vertical line test produces a function as defined here that obeys all the properties required of it in that definition and is also similarly compatible with definition 338. So before I go through the proof, let me read out the footnote that he has for that question. Let's see. He says, note that this definition is not circular because the notion of a function was not used to define ordered triples or a Cartesian product of two sets. So that's the footnote that the star was referring to there. Okay, here's my proof. Right, let xy be sets and let p of xy be a property relating to each x in x to relating each x and x to a y and y such that p of xy is true and p satisfies the vertical line test. Then let g be a subset of x times y such that xy is in G if and only if p of xy is true. Then G satisfies the vertical line test by definition. Furthermore, p of xy defines a function f from x to y, so y equals f of x if and only if p of xy is true, if and only if xy is an element of G. So that proves that it's compatible with where was it? With definition 331, and then definition 338 I show is compatible also. That follows from the previous parts of the question, right? And that's the proof. Okay, 3.5.11 show that axiom 311 can in fact be deduced from lemma 3.4.10 and the other axioms of set theory, and thus lemma 3.4.10 can be used as an alternate formulation of the power set axiom. He does give a hint here. He says for any two sets, x and y, use lemma 3.4.10 and excuse me, and the axiom of specification to construct the set of all subsets of x times y which obey the vertical line test, then use exercise 3.5.10 and the axiom of replacement. So I did that down here. Here's my proof. Let xy be sets, then by lemma 3.4.10, p of x, the power set of x times y is a set, and S is, if I define S to be the set of all subsets of the power set that satisfy the vertical line test, if then S is a set by the axiom of specification. Next, define the set F of all ordered triples, X, Y, G, where G is an element of S. which is a set by the axiom of replacement, then if f, sorry, this should be f equals. If f equals the order triple xyg is a function from x to y as defined in exercise 3.5.10, then again, this should be, sorry, there's a typo here. Then this order triple is an element of the set F. Also, if x, y, g is an element of the set F, then for any x and x, there's a unique y and y such that x, y is an element of G. Therefore, sorry, I forgot the equal signs in all of these. F equals x, y, g is a function from x to y, then y to the x equals the set F. All right, so that shows that problem 3. So actually, let me go back here. If you go back to the video for my solutions to the exercise set 3.4, I said that I skipped part 2 of question, what number was this? 346. I did part 1, but I skipped 3 point. Sorry, I skipped part 2 because basically he wanted us to show what we just did in that exercise that I just went over in 3.5. So I skipped it because he's, he doesn't define ordered pairs or Cartesian products until 3.5. So I skipped it, but now we have the proof, which means that actually I can fill in the proof now for 3.4.7 because he said this proof, you have to use the previous proof. So let me just read it out again just to remind everybody. Question 3.4.7 says let x, y be sets. Define a partial function from x to y be any function f from x prime to y prime, whose domain is x prime is a subset of x, and whose codomain y prime is a subset of y. Show that the collection of all partial functions from x to y is itself a set. And he gives a hint here. He says use exercise 3.4.6, the power set axiom and the replacement axiom and the union axiom. So here's the proof. By exercise 3.4.6, the set of all subsets of x and the set of all subsets of y are sets. Also, for any fixed y prime in a subset of y prime to the x prime is a set for each x prime in x. Furthermore, the set of all y prime to the x prime is such that x prime is a subset of x is a set by the axiom of replacement. And then lastly, take the union of all those, and that's guaranteed to be a set by the axiom of union. So that shows that the set of all partial functions from x to y is a set. Okay, so we've gone through all the problems. We've filled in the ones we left out in the previous section. All right, going on to 3.5.12. There were some problems with one because there's some typos, but let me read through it first. Exercise 3.5.12 says this exercise will establish a rigorous version of proposition 2.1.16 that avoids circularity, in particular avoiding the use of any object that required proposition 2.1.16 to construct. So part 1 of the question says this: let x be a set, let f from n times the Cartesian product n with x to x be a function, and let c be an element of x. Show that there exists a function. Now here's where the typo is. So in the book, he says the function should go from x to x. It should actually be from n to x, not x to x. So that's a typo that's actually in the book. So if you have the 4th edition, just be aware of that. This function a has to go from the natural numbers to the set x, not the set x to the set x. Such that a of 0 equals c, and a of n, a of the successor of n equals f of n, a of n for all n and n, and furthermore, this function is unique, right? He does give a hint for this because the proof is actually quite involved. So first show inductively by a modification of the proof of lemma 3.5.11 that for every natural number n and n, there exists a unique function an from the set n and n less than or equal to n to the set x, such that a sub n of 0 equals c, and a sub n of the successor of n equals f of n, comma a sub n of n for all n and n, such that n is less than n. All right, so we do that with a proof by induction. We induct on capital N and n. So sorry, I gotta readjust again. For n equals 0, 0 comma c is an element of the Cartesian product of n times x. And then I want to define a0 to be the function that goes from the set n and n less than or equal to 0 to x by a sub 0 of 0 equals c. And that obviously satisfies the specified conditions. And also a0 of 0 is unique because, there's only one element going to one element. So then we go to the inductive step. Assume there is n in capital N, such that there is a function a sub n from the set n in n less than or equal to n to x, where a n of 0 is c, and a sub n of n, the successor of n, is equal to f of n, comma a sub n of n, right? Then a sub n of I is unique for each I from 0 to n, since c is unique and f is a function. In particular, a sub n of n equals f of n minus 1, comma a n n minus 1 exists and is unique. Then the finite sequence c a n 1 a n 2 dot 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 up to a n n, comma f n a n of n is an element of the Cartesian product of the set x with itself n n plus plus times, right? By finite choice, then we can define the function a n plus plus to be this means successor, by the way, but it's easier to say n plus plus, from the set n in n less than or equal to n plus plus to x, such that a n plus plus of I, sorry, the sequence of those things is that sequence that I talked about above. Then a n plus plus is 0 is equal to c, and a n plus plus of little n plus plus is equal to f of n, a n of little n, for n plus plus between 1 and capital N plus plus. Therefore, there is a unique function a n from n and n less than or equal to n to x, where a n of 0 is c, and a sub capital N of n little n plus plus equals f of n, comma a sub capital N of n for all capital N and n by induction. Okay, so that, like I said, that's sort of the involved part there. So that family of functions exists. And now here's the reason that we went through that work. So I want to define my function a from n to x, such that a of 0 equals a0 of 0, and a of the successor of little n is equal to a sub the successor of little n of the successor of little n. So that's what you need for little a. That's the definition that you want. And let's show that it works. So then a of 0 is a of 0, 0, which is defined to be c. And a of the successor of little n is equal to the function value of a sub the successor of n evaluated at the successor of n, which by definition is f of n, comma the a sub the successor of little n evaluated at n, which is actually the same number as a subscript little n of n, because of the way that we constructed the sequence of n tuples, which is equal to f of n of a n. By the way, we defined the function a for any n and n. Furthermore, each a of n is unique, since c is unique and f is a function. Okay, that's part one. In part two, he gives a warning. He says this is challenging. I'm not sure why he says that, unless maybe I did something wrong here, but this part seemed easy compared to part one. So I don't know. Maybe it depends on who's doing it, but he gives a warning here that part two is challenging. So let's actually read it out, and then I'll show you my proof. So prove one without using any properties of the natural numbers other than the Peano axioms directly, in particular without using the ordering of the natural numbers and without appealing to proposition 2.1.16. And he gives a hint. So first show inductively using only the Peano axioms and basic set theory that for every natural number n in capital N and n, there exists a unique pair a sub capital N, b sub capital N of subsets of the natural numbers, which obeys the following properties. And then there's a bunch of properties here. They want the intersection to be empty, the union to be all of n. They want 0 to be an element of an, the successor of capital N to be an element of Bn. Whenever n is an element of Bn, we have the successor of n in Bn. And finally, property F, whenever n is an element of An and n is not equal to capital N, we have the successor of little n is an element of A sub capital N. Once one obtains these sets, use An as a suitable, use A sub capital N as a substitute for the set n in n and less than or equal to capital N in the previous argument. So like I said, I don't know why he gives this warning here. Just from my experience, question 1 was a little more challenging than question 2, but I don't know, your mileage may vary. I don't know. So here's the proof. We proceed by induction on n. Base step, capital N equals 0. Let A, here I'm just defining the set. So A0 is the set containing 0, and B0 is the natural numbers minus 0. Then, as you can check, all the properties that he wants holds, right? So then the base step is satisfied. The inductive step, assume such set AN, BN exists for some capital N and N, and define A sub successor of capital N to be the union of A sub capital N with the singleton set containing the successor of capital N, and B sub the successor of capital N is B sub capital N minus the singleton set containing the successor of capital N. Then again, I'm just checking the properties here. The intersection is empty just by the definition, the way we define the sets. The union of the two sets is n. 0 obviously is an element of an, which implies that 0 is an element of the A sub the successor of n. The successor of the successor of n is an element of Bn, implies that the successor of the successor of n is an element of B sub the successor of n, and so on and so on. All these you can just see all the properties are satisfied. This property follows from one of the axioms, so maybe I should read this out. N is an element of B. N is an element of B sub the successor of capital N, implies N is an element of Bn minus the singleton set containing the successor of capital N, which implies that N is not the successor of capital N, and N is an element of B sub capital N, implies the successor of little n is an element of B sub the capital N, which implies that the successor of little n is not the successor of capital N by axiom 2.4, and the successor of little n is an element of B sub the successor of capital N. Sorry, I don't even know if people are able to follow this. It might be better just to pause the video and just read through the proof yourself. But lastly, if n is not the successor of capital N, then n is an element of A sub the successor of capital N, then n is an element of A sub capital N, implies the successor of little n is an element of A sub capital N by inductive hypothesis, which implies that the successor of little n is an element of A sub the successor of capital N. Therefore, for any capital N and N, a pair of subsets A sub capital N, B sub capital N, satisfying properties A through F always exist by induction. And then just replacing each instance of the domain of the A sub n's from the previous part by A sub capital N for each n and n in the proof in part 1 proves the proposition. Right, so that proves part 2. And then there's a part and then there's the next question which relies on that one. So 3.5.13, which is the last question in this section. Like I said, I warned you at the beginning, this was a long exercise set. So okay, let's read it out first. The purpose of this exercise is to show that there is essentially only one version of the natural number system in set theory. For example, the discussion in remark 2.1.12. Suppose we have a set n prime of alternate natural numbers and alternate 0, which we'll denote by 0 prime, and an alternate increment operation, which we'll call plus plus prime. which takes any alternative natural number n prime and capital N prime, and returns another alternate natural number n prime plus plus prime in n prime, such that the Peano axioms, which are axioms 2.1 to 2.5, which we did a long time ago, all hold with the natural numbers 0 and increment replaced by their alternative counterparts. Show that there exists a bijection f from n to n prime from the natural numbers to the alternative natural numbers, such that f of 0 equals 0 prime, and such that for any n and n, at n prime and n prime, we have f of n equals n prime if and only if f of the successor of little n is equal to the alternate successor of the alternate n prime. And then he gives a hint. He says use exercise 3.5.12. So let's go through it. This is the last problem. Let A be the function from n to n prime, be defined as in exercise 3.5.12. That's the one we did above the previous one, where C is, I'm going to let C equal the 0 in n prime. So 0 prime is equal to C. Right, so f from n times n prime to n prime is the function fn m prime equals m prime plus plus prime. Then a of 0 equals a prime, and if a of n equals n prime, then a of the successor of n equals a sub the successor of n. Sorry, this is so hard to say. A of the successor of little n is equal to a sub the successor of little n evaluated at the successor of little n. This is the way that we defined a in the previous problem, if you remember, which is equal to f of n a n, which is equal to a of n plus plus, which is equal to n prime n prime plus plus. It should be, sorry, there's a typo here. This should be, whoops, prime n prime. And if an plus plus is equal to n prime plus plus prime, then n prime plus plus prime equals f of n a comma a n, which is equal to a of n plus plus prime, which implies that a of n equals n prime by axiom 2.4. And then lastly, we have to show that the function a is surjective. Is bijection. So we have to show it's surjective and injective, which I did by using axiom schema 2.5, which is the induction axiom. So A is surjective. Is there a double S there? A is surjective since, let me just erase this. This shouldn't be here. Since 0 prime equals A of 0, and assuming n prime equals A of n for some n prime in n prime in capital N prime, then n prime plus plus prime equals A of n plus plus. Sorry, I forgot. There's too many primes floating around. There should be a prime here. Equals f of n, a of n equals a of n, the successor of little n. Then surjectivity follows from axiom schema 2.5. Right. So in other words, it follows by induction. Right, and then similar type of proof for injectivity. A is injective since 0 prime is not the successor of any n prime and n prime, and a of 0 equals 0 prime. And assuming that a of n equals n prime equals a of m, that implies that n equals m for some n prime in n prime, then a of the successor of little n equals a of the successor of little m, implies f of n a sub little n of n equals f of m, comma a sub little m of m, which implies that a sub little n of n equals a sub m little m of m, which implies that a of n equals a of m, which means that n is m by inductive hypothesis, right? Which implies that the successor of n, little n equals the successor of little m by axiom 2.4. Therefore, A is injective by axiom schema 2.5. Therefore, A is a bijection. So that shows that we have a bijection from the natural numbers to the alternate natural numbers. What that means essentially is that there's only one set of natural numbers. Okay, so let me just stop the screen and share here for a second. That was a rough ride. If you made it to the end here, congratulations. this like I said, this was kind of some of the problems in here were a bit tricky. But we got through them, and now we can move on to the next section, which is the final section of chapter 3. And then finally we can move on to chapter 4, which I'm looking forward to. Section 3.6 is on cardinality of sets. So I'm hoping that I'll be able to actually do the summary for it tomorrow, like work it out and then post the video for it tomorrow, but that might be too ambitious. I don't know, but I'll try. I'll try my best. If not, it'll be up, sometime this week. So I'll see you guys in the next video. Thank you for watching and sitting through me saying N prime and capital N prime and all the other junk. And I'll see you guys in the next video. Keep learning until that time, everybody.